Hello students. Today we will be discussing about hybridization. As we know, this hybridization is one of the important most topic they are there in chemistry. And from this hybridization, in every exam, whether it's 11th or 12th or IIT or NEET, questions they will be asking. This hybridization plays very important, very crucial role to understand chemistry. You know what hybridization is? Hybridization is related to covalent bonding only. We know in ionic bonding or electrovalent bonding, transfer of electron is there. One atom, one element will be losing electron, or you can say one electropositive element will be losing electron and one electronegative element will gain that electron. In this way, ionic bond takes place. Ionic bond is very easy to understand, but covalent bonding is very vast, very big, and no one concept is sufficient to explain it completely or to justify it completely. So many different concepts related to this covalent bonding is there. Valence bond theory is there, but valence bond theory is unable to explain paramagnetic nature of oxygen. So the need was there to explain the paramagnetic nature of oxygen. So molecular orbital theory was given. Even after this VBT, MOT, VSEPR, resonance, none of them are quite sufficient to explain hybridization, even odd electron bond too. So hybridization was given to explain that covalent bonding properly or completely. See what hybridization is. Hybridization is simply a process of mixing of two or more atomic orbitals of approximately same energy level. Hybridization is simply a process of mixing of two or more atomic orbitals of approximately same energy level to form hybrid orbitals. When two or more atomic orbitals combine together, and those atomic orbitals must be approximately of same energy level, then only they can combine. Otherwise, they will not combine with each other. So such orbitals which are formed by the combination of approximately same energy atomic orbitals are called hybrid orbitals. And this process of mixing of approximately atomic orbitals of approximately same energy level, that process is called hybridization. See here in this is one atomic orbital, this is another, this is third one. These three atomic orbitals combine together. These three atomic orbitals combine together to form three hybridized orbital. Three hybridized orbital. Since one atomic orbital was S and these two are p atomic orbitals, so hybridized orbital formed will be sp2 because one s and two p na, so it will be sp2 hybridized orbital. So the number of hybridized orbitals formed will always be equal to the total number of atomic orbitals combining together. Since here one s and two p atomic orbitals were there, so the hybridized orbital formed will be sp2. See, what's the difference between hybridized orbitals and molecular orbitals? Hybridized orbitals, you can say when atomic orbitals are not ready to take part there in the bond formation, so we'll provide them energy, we'll get them excited so that they will be ready to take part there in the bond formation. So these hybridized orbitals are formed by the excitation of atomic orbitals, and by the combination of atomic orbitals, molecular orbitals will be formed. See here, more than one atomic orbitals are getting excited and then combining together to form hybridized orbitals. But in molecular orbitals, only atomic orbitals they are in ground state will combine together to form molecular orbital. These hybridized orbitals are relatively more stable than atomic orbital. Hybridized orbitals are relatively more stable than atomic orbitals, but molecular orbitals may be less or more stable than the atomic orbitals. That depends. That we will do there in molecular orbital theory video. then hybridized orbitals will have greater energy than atomic orbitals, while molecular orbitals may have less or more than atomic orbitals. The energy of molecular orbital may be less or more than the atomic orbitals. Hybridized orbitals will always be bonding in nature. There is no question of opposing bond formation there in hybridization. So only bonding orbitals will be there. While in case of molecular orbitals, it can be bonding or can be anti-bonding. hybridized orbitals will always be hybridized orbitals will always be monocentric. Means in hybridization, since atomic orbitals of approximately same energy level from one atom only will be taking part. Since there only one atom is involved, so obviously there will be one nucleus. So in case of hybridized orbitals, monocentric orbitals will be taking part, while in case of molecular orbital theory, since many atoms will combine together, so obviously there will be participation of many nucleus. So it is polycentric, while hybridized orbitals will always be monocentric only. So this was about the hybridization basic idea, or you can say definition, and how it is hybridized orbital is different from the molecular orbital. This was related to this all. Now we can classify hybridization into different classes on the basis of number of atomic orbitals taking part. If one s and one p only combines together to form hybridized orbital, then that hybridization will be known as sp hybridization. If one atomic orbital of s and two p atomic orbitals will be taking part, then the hybridized orbital formed will be sp2. Like this, if one s and three p atomic orbitals combine together to form hybridized orbital, then the hybridized orbital formed will be known as sp3. Like this, sp3d, sp3d2, sp3d3. That's all. So one by one, we'll discuss all these different types of hybridizations. First, we will discuss about sp hybridization. See if one s and one p atomic orbitals combine together to form sp hybridized orbital. To form sp hybridized orbital. This is one s and this is one p, and they will combine together to form. This is one sp, this is another sp. Sp hybridized orbitals. So see here, this one s and one p orbital combine together to form sp hybridized orbital. This sp hybridized orbital is linear in shape. Its bond angle will be 180 degree, and hybridization will be known as sp hybridization. Hybridization will be sp hybridization. So these two atomic orbitals, s atomic orbital and p atomic orbital, must be of same energy level. Then only they can overlap each other and will form sp hybridized orbital. These two, this is sp hybridized and this is also sp hybridized orbital. So this is about sp hybridization. In this sp hybridization, s is 1 and p is also 1. In this sp hybridization, one s and one p is there. So s character will be 50% and p character will also be 50%. So 50% s character and 50% p character will be there. We know more the percentage s character, more will be the percentage S character will be directly proportional to electronegativity, is directly proportional to acidity, is directly proportional to polarity, is directly proportional to dipole moment, is directly proportional to dipole moment. So this is about SP or linear or diagonal hybridization. The best example for this SP hybridization, how you will come to know which example you should take. So see, this is Spina. So one element will be there from S block and second element must be there from P block. One element must be there from S and second must be there from P block. So see, element which is there in S block and have the tendency of forming covalent bonding will be hydrogen only. So this S block element which will form this Sp hybridization, which will show this Sp hybridization, one element will be hydrogen and second element we can take from P block. You can take Cl from P block. So HCl, the best example for this will be HCl. In this HCl, Sp hybridization will be there, will be present. Now see, our second example will be Sp2 hybridization. As I already told you this all 180 degree and this all. Now see, BeH2, we'll be discussing Sp2 hybridization laterwards. First we'll continue the same, that Sp hybridization, therefore alkyne also. In alkyne, this is alkyne, this is alkyne, this is ethyne, C2H2, that is ethyne. Here see, this carbon is having 1 sigma and 1 sigma. This carbon is having 2 sigma. 2 sigma means Sp hybridization. In case of organic chemistry, we can come to know about the hybridization by counting their number of sigma bonds. If 2 sigma bonds, then Sp hybridization. If 3 sigma bonds, one atom will be having, then it will be Sp2. And if 4 sigma bonds around a single atom is there, then it will be showing Sp3 hybridization. So this method is applicable only for organic chemistry, where you will be considering sigma bonds only, and from there you will come to know about the hybridization shown by that specific element. So since here in this carbon 2 sigma bonds are there, this carbon is also showing 1 and 2 sigma bonds, so we'll be showing Sp hybridization. So this alkyne will also be showing Sp hybridization. Bond angle will be 180 degree and their geometry will also be linear. Their geometry will also be linear, or you can say diagonal. Diagonal hybridization or linear hybridization, it will be shown. Now see, one carbon is having 4 electrons there in their valence shell. Another carbon will also be having 4 electrons there in valence shell. These 3 unpaired electrons of carbon will overlap these 3 unpaired electrons of another carbon. And this 1 unpaired electron of carbon will be overlapping 1 unpaired electron of hydrogen. In this way, 2, 4, 6, and 8 electrons are there in this carbon atom. What about this hydrogen? This hydrogen having 1 unpaired electron will overlap this 1 remaining unpaired electron of carbon, and in this way, unpaired electron of hydrogen will also get paired. What about this carbon? This carbon will overlap these 3 unpaired electrons of this carbon will overlap these 3 unpaired electrons of another carbon atom, and this 1 unpaired electron of carbon will overlap 1 unpaired electron of hydrogen atom. In this way, 2, 4, 6, and 8 completely filled octet this carbon is having. What about this hydrogen? This hydrogen will also be having paired electronic configuration. In this way, between this carbon and this carbon, 6 electrons are shared. That's why you'll be forming triple bond. For the formation of one covalent bond, 2 electrons are required. If 6 electrons are there, means there will be triple bond between them. And between this carbon and hydrogen, single bond, and this carbon and hydrogen also single bond. So in case of C, triple bond C, their bond length will be 120 pm. Their bond length will be 120 pm. As I already told you, bond angle will be 180 degree, and 1 sigma. This 1 is sigma and remaining 2 are pi bonds. So 1 sigma and 2 pi bonds between 2 carbon atoms will be there. C, electronic configuration of carbon is 1s2, 2s2, 2p2. This 1 electron from 2s, 1 electron from 2s will be shifted to 2p, making 1s and 3p atomic orbitals. And after overlapping, after combination, there will not be any s or any p orbital. They will combine together to form 4 sp hybridized orbitals. 2 sp hybridized orbitals, and remaining 2 p atomic orbitals will be there. These 2 sp hybridized orbitals will be forming sigma bond, and these 2p atomic orbitals will be forming pi bond. So, and as we know, in hybridization, we will never consider pi bond. We will consider only sigma bond. So this is electron dot structure. This is structure which I wrote here. That is electron dot structure, and this is graphical structure. This Lewis electron dot structure. This structure was given by Lewis. So this is a Lewis electron dot structure, and this is Cooper's graphical formula. Cooper's graphical formula. Now, this was all about sp hybridization. Now we'll take sp2 hybridization. Now we'll discuss about sp2 or planar hybridization. As I already told you, if 1s and 2p atomic orbitals are combining together to form hybridized orbital, then that hybridization will be known as sp2 hybridization, or you can say planar hybridization, or you can say planar hybridization. So see, this is 1s, this is 1p, this is another p. These three will combine together to form sp2 hybridized orbital. sp2, sp2, sp2 hybridized orbital of any species. Now see, in this sp2 hybridization, S is 1 and P is 2. So out of 3 total, this S is one part, that is 33% S character and 67% P character. 33% S character and 67% P character. And their shape will be trigonal planar. Bond angle will be 120 degree. 120 degree, and shape will be trigonal planar. So the example for this is C double bond C. This is an example from organic chemistry. 1, 2, and 3 sigma. 3 sigma means sp2 hybridization. As I told you, on the basis of number of sigma bonds, we can count hybridization, or we can come to know about hybridization. So this is an example of sp2 hybridization. Other than this, you can take boron also. Boron also in Boron also. In boron also, boron is atomic number 5. Electronic configuration will be electronic configuration will be 5, that is 2s2 2p 1. This one electron from 2s will be shifted to 2p. In this way, this will be showing sp2 hybridization. 1s and 2p atomic orbitals now will combine together to form sp2 hybridization. sp2 hybridization, that is what I wrote here. 1s and 2p. 2p. These three will combine together to form sp2 hybridized orbital. Each sp2 hybridized orbital will be having one unpaired electron and one hydrogen atom. One hydrogen atom will also be having one unpaired electron. One hydrogen atom will be having one s atomic orbital, and in that one s atomic orbital, one unpaired electron will be there. In this way, three sp2 hybridized orbitals of boron, each having one unpaired electron, will combine with three 1s atomic orbital of hydrogen to form BH3. To form BH3. The shape is trigonal planar. The shape is trigonal planar, and bond angle will be 120 degree, and hybridization will be sp2. So this is about the hybridization shown by boron in BH3 and carbon in CH2. So this was about boron in BH3 and carbon in CH2H2. You know, carbon is 6, that is 1s2, 2s2, 2p2. This is 2s and this is 2p. This is 2s and this is 2p2. This is in ground state, and in excited state, this one electron from 2s will be shifted to 2p, making its configuration 2s1 and 2p3. 2s1 and 2p3. In this way, this sp3 hybridized orbital of carbon will be there. If two sp hybridized orbitals will be taking part, they are there in the bond formation, then that will be sp hybridization. If three sp hybridized orbitals will be taking part, they are there in the bond formation, then it will be sp2 hybridization. And if 1s and 3p, all the four sp3 hybridized orbitals are taking part there in the bond formation, then it will be sp3 hybridization. So it depends whether all the four sp hybridized orbitals will be taking part, then it will be sp3. If 3sp means 1s and 2p atomic orbitals, hybridized orbitals are taking part there in the bond formation, then it will be sp2 hybridization, and one remaining p orbital will be forming pi bond. If 1s and 1p atomic orbitals will be taking part there in the bond formation, then it will be sp hybridization, and remaining 2p atomic orbitals will be taking part there in the pi bond formation. So on the basis of number of p, because s in all the three cases will remain the constant, there will only be difference in number of p orbital, which will be determining whether carbon will be showing sp or sp2 or sp3 hybridization. If 1s and 1p will only be taking part there in the hybridization process, then remaining 2p atomic orbitals will be forming pi bonds. If 1s and 2p atomic orbitals of carbon will be taking part there in the process of hybridization, means will be hybridized orbital, then only one p orbital, atomic orbital, will be remaining, and that will be responsible for making pi bond. While in case of 1s and 3p orbitals, if all the four are taking part, they are there in the process of hybridization, then there will be no p atomic orbital which will be taking part there in the hybridization, and that sort of hybridization will be known as sp3 hybridization. So this was example of sp2 hybridization, both these two. Now the next one is sp3 or tetrahedral hybridization. As I already told you, carbon 6, 2s1, 2px1, 2py1, and 2pz1. These four atomic orbitals will combine together to form four sp3 hybridized orbitals. See in this carbon, these four sigma bonds are there. These four sigma bonds means will be showing sp3 hybridization. So in CH4 or in CCl4 means whenever carbon-carbon single bond is there, then hybridization shown by that carbon will be sp3. If carbon-carbon double bond is there, then carbon will be showing sp2 hybridization. If carbon-carbon triple bond is there, then that carbon will be showing sp hybridization. So this is about sp3 hybridization. This is about sp3 hybridization. Now the bond angle there in sp3 hybridization will be 109.5 degree. Shape will be tetrahedral. And what about the percentage S character? S will be 25% and P character will be 75%. As I already told you, more the percentage of S character, more will be the electronegativity, more will be the acidity, more will be the polarity, more will be the dipole moment. Like this, many more points are there, which we are not going to discuss here in this part of chemistry, that we will be doing there in General Organic Chemistry, GOC. So in sp3 hybridization, there is no question of any pi bond between two carbon atoms. All the four bonds will be single bond and pi bond won't be there. So there will not be participation of any p atomic orbital there in the process of hybridization. They can ask you this question also in sp2, sp3 hybridization, in which case there will not be participation of any p atomic orbital there in the process of hybridization. So it is sp3 hybridization in which there is no participation of p atomic orbital. sp3 hybridized orbitals are taking part, but there is no p atomic orbital which is taking part there in the bond formation, because as I already told you that p atomic orbitals can take part there in the process of formation of pi bond only. And in case of CH4 or in case of sp3 hybridization shown by carbon, since there is no pi bond, so there is no question of participation of p atomic orbitals there in the process of hybridization. So this is all about sp3 hybridization shown by carbon there.